In this video, we're going to prove one of the most important results and theorems in statistics, that is to prove the independency of the sample mean and the sample variance. This, of course, has a lot of applications, and in fact, is one of my favorite theorems because if you notice, these two estimators depend on the variables of the random sample and they turn out to be independent, right? So we are going to follow along the proof in the Statistical Inference book from Casella. And if you notice, it's in the section 5 and it's not too in detail or explained. So any comments, let me know right below and I'll try to answer as soon as possible. So let's go with the proof.
So the theorem says let x1 up to xn be a random sample, and recall that because it's a random sample, we know that these variables are independent and identically distributed variables, denoted by IID, of a normal distribution with population mean mu and population standard deviation sigma, not sigma squared, my bad. And let by definition x bar, the sample mean, be the sum of these random variables divided by the size of the sample, that it's n. And same by definition, let the sample variance s squared be n divided by n minus 1 times the sum from I equal to 1 up to n of xi minus x bar squared. Okay, so we want to prove that the sample mean x bar and the sample variance are independent random variables. I'm gonna let it like RV. Okay, so let me just put here that this is the sample mean and this is the sample variance. Sample, not population. Okay, so let's begin with the proof. So by definition of the sample variance, we know that s squared is 1 divided by n minus 1 times the sum from I equal to 1 up to n of xi minus x bar squared. Okay, so let's expand the sum. Let this factor out, and this is going to be x1 minus x bar squared plus, and now the limits are going to change. I is going to start from 2, not from 1, because we just take the first factor out, right? So let's make use of the fact that we know that the sum from I equal to 1 up to n of xi minus x bar is 0. And this is pretty simple to see because if we expand this is going to be x1 minus x bar plus x2 minus x bar up to xn minus x bar. Okay, so if we group this is going to be x1 plus xn plus, and this is going to be nothing more than n times the negative x bar. Okay, but if we multiply this by n and divide it by n, this is nothing less than the definition of the sample mean. So we have an x bar minus n times x bar, that this is 0, right? So let me make it smaller. No. Okay, just I will leave it like that. And continuing, this is going to be, well, I let this factor out and replace x1 minus x bar with the sum from I equal to 2 up to n of xi minus x bar squared plus the sum from I equal to 2 up to n of xi minus x bar squared. And this is because of the fact we just saw, right? Because if we let x1 minus x bar be alone, this is going to be the negative sum of this, right? And because this factor was squared, then the negative sign don't affect us, so I just ignore it. So hence, we had in the beginning that the sample variance was a function of x1, x2, x3, up to xn, but now we find a way to express this function as just a function of the variables x2 up to xn. So this is a important concept that we're going to use at the end, but just notice here and keep this in mind that it's going to be important. Okay, so now let's focus on the joint PDF probability density function of x1 up to xn. Okay, so without loss of generality, we are going to assume that sigma is going to be 1 and the population mean is going to be 0. This is, we have a population from a standard normal distribution. So because of this, we know that the PDF for each variable is going to look something like this. 1 divided by the root of 2 times pi of e to the minus 1 half xi. Okay? So because, let me just notice here that we assume this without loss of generality because of the theory of the location scale families that comes in the book and the section 3. So if you guys want me to explain it later, let me know in the comments. But from IID, we know that the joint PDF of x1 up to xn is the product of the PDF for each variable, right? So to find it, we're going to multiply n times the PDF for each variable. So this is going to be to the power n, e to the minus 1 half, x1, dot, 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 e to the minus 1 half, xn, right? And this is nothing less than 1 divided by 2 times pi to the n divided by 2 times e to the minus 1 half and the sum of the random variables from I equal to 1 up to n. And this is because of the properties of exponential functions, right? Remember that a to the m times a to the n, because they're the same base, this is a to the n plus m. Okay, so now we will use this result later. And here, just notice that the domain is all the real numbers. So now here's where the magic comes, and we're going to make a transformation, a PDF transformation in a way that we are going to define y1 equal to x bar, y2 equal to x2 minus x bar, y3 is going to be x3 minus x bar, and so on up to yn is going to be xn minus x bar. Okay, so notice here that xi is equal to yi plus y1, and y1 is x bar, right? And this is for all I in the range of 2 up to n. Okay, so by the theory of transformations, we know that we have to find the determinant of the Jacobian matrix, that by definition is the determinant of a matrix of partial derivatives with respect to the new variables that we just defined. So the partial derivative respect y1 of x1, the partial derivative respect y1 of x2 and so on. So just let me write this fast. So now we're wondering what is the value of this determinant, right? So we have to find the partial derivatives. But first we have to know who is x1. So we already saw this in the beginning of the video, that x1 minus x bar is going to be the negative sum from I equal to 2 up to n of xi minus x bar, right? So x1 is equal to x bar, we just pass this on the other side, minus the sum from I equal to 2 up to n of this value, xi minus x bar. But because the way we define xi, so we notice that xi is equal to yi plus y1, but xi is minus y1 is equal to yi. Xi minus x bar is equal to yi. Okay, so this is exactly what we're looking for because we just replace its value by yi. So yi, and we notice that x bar is nothing less than y1, right? So this is y1 minus, so if we expand this is y2 plus y3 plus up to y, and this is x1 is equal to y1 minus y2 minus y3 minus yn. Okay, so now we can find the partial derivatives. The partial derivatives with respect y1 of x1 is 1. Now the partial derivative with respect y2 of x1 is going to be minus 1, and similar with the rest. Minus 1, and so on. So the partial derivative with respect yn of x1 is going to be minus 1. Okay, so now let's find who is x2. Okay, so by the way we define these variables, we know that y2 is equal to x2 minus x bar, right? And this is x2 minus y1. So x2 is going to be y2 plus y1. Okay, so now we can find the partial derivative with respect y1 of x2, and this is going to be 1. The partial derivative with respect y2 of x2 is going to be 1. So we notice that the partial derivative with respect yj of x2 is going to be 0 if j is not 2 or 1. Okay, so now let's see who is x3. Similar case, we know that x3 is y3 plus y1. So the partial derivative with respect y1 of x3 is going to be 1. The partial derivative with respect y1 of x3 is going to be 1. And similar case, the partial derivative with respect xj of x3 is going to be 0 if j is not 3 or 1. And the same happens with x4, that is equal to y4 plus y1. Okay, so now we can fill our Jacobian determinant that by definition, this is going to be the determinant of 1, 1, 1 up to 1. So notice that all of these column is going to be 1. And just let me put the numbers here, the number of the rows and columns. And this is minus 1 up to minus 1. This is 1, 0, 0. This is 0, 1 up to 0, and so on. This is going to be 0. This is going to be 0. This is going to be 1, and so on. Okay, so this is more easy to compute, but we still wonder what is the value of this determinant, right? So to see this in a simple way, let n be 4. So the determinant, if n is 4, this is going to be 1, 1, 1, 1, minus 1, 1, 0, 0, minus 1, 0, 1, 0, and minus 1, 0, 1. Okay, so this is more easier to compute and to see what is going to result now. So let's this be my columns up to C4. And by properties of the determinant, we know that we can add any column or row to any other column or row without changing the value of the determinant. So let it be C1 minus C4, and this is the column vector of 1, plus, I'm just going to reverse the sign. So the 4 column is going to be 1, 0, 0, minus 1, and this is going to be 2, 1, 1, 0. So this is our new value for the first column, right? So we're going to make the same with the other columns. C1 minus C3 is going to be the plus. I'm going to let this like that, reverse the sign, and this is going to be 3, 1, 0, 0. So again, this is going to be our new value for the first column. So at the end, we're going to have, no, it's 4, sorry. 4, 0, 0, 0, and the other columns stay as the same. Minus 1, 1, 0, 0, minus 1, 0, 1, 0, minus 1, 0, 0, 1. So by the Laplace expansion, we can compute this in a simple way, right? So this is going to be 4 times the determinant 1, 0, 0, 0, 1, 0, 0, 0, 1. And notice that this is the identity matrix, right? And we know that the determinant of this special matrix is going to be always 1. Minus times minus 1 times the determinant of 0, 0, 0, 0, 1, 0, 0, 0, 1, okay? Plus minus 1, this is going to be 0, 0, 0, 1, 0, 0, 0, 0, 1. And finally minus 1 times the determinant. We already know that these determinants are going to go to 0, but let me just write it out. So because these determinants have one column that is all 0, we know by properties of determinant is going to be 0, and this is going to be 1. So at the end, we will have this like 4 times 1, that is 4, is equal to n. So you can prove this whatever way you want, but the value of our determinant is going to be nothing less than n. So by theory of PDF transformations, we know that this Jacobian is going to multiply our PDF, our joint PDF. That is what we found at the beginning. So this is going to be e to the minus 1/2. And we replace these values that we found, plus I equal to 2 of its I squared. Okay, and notice that xi is y1 plus yi. This is because we have to replace our variables with the new variables we just defined in terms of y's. So this is going to be n divided by 2 times pi to the n-half e to the minus 1/2, and x1 is going to be y1 minus the sum of the yi's squared, I equals 2, plus the sum from I equals 2 up to n of y1 plus yi squared. Okay, so more algebra. The last thing, we are going to focus on this exponent. We are going to expand this, expanding this. So we have that y1 squared minus 2 times y1 times the sum from I equal to 2 up to n of yi plus the sum of the yi's squared. We're just expanding this power, right? So on the other side, we have the sum from I equal to 2 up to n of y1 squared plus 2 times y1 times yi plus yi squared. Okay, so expanding this last term, we have yi squared minus 2 times y1 times the sum from the yi's from I equal to 2 up to n plus the squared sum of the yi's from I equal to 2 up to n plus, so this is constant, but we're going to let it in this way for a simple way to see it, right? So this is times the sum yi's from I equal to 2 up to n plus the sum from I equal to up to n of the yi squared. So we have this fourth term that is constant. So by convenience, we are going to make the limit start from 1, and we're going to subtract it to not alter the sum. So we can cancel the first term with the last term. So we have this goes with this with this by. So we have left that this is ny1 squared plus the sum from I equal to 2 up to n of yi, this all this squared, plus the sum from I equal to 2 up to n of xi squared. Okay, so now let's replace this in our PDF, in our joint PDF. So notice here that we are going to leave it in a way that we can simply see that this is a multiplication of functions that depend only on yi and the other ones from yi equal to 2 up to n, and divided by 2 y1 squared times e to the minus 1/2 the sum y equal to 2 up to n yi squared plus, this is by properties of exponentials, right? Okay, so this first term is a constant. It doesn't matter, even though we spend a lot of time finding the Jacobian. So we see that this function is just in terms of y1. And as we define y1, that is x bar. And the second term is a function in terms of y2 up to yn. That is a function of x2 minus x bar up to xn minus x bar. And this is by theorem of independency. We can see that as we can factor these PDFs, we can conclude that these variables are independent, as the sample variance is a function of x2 minus x bar up to xn minus x bar. So